Thank you very much for coming, ladies and gentlemen. And I'd like to extend a warm welcome to those of you watching online, as well as those of you in the room and those of you in the overflow room downstairs. Before I introduce Nick, I'd just like to do a little bit of housekeeping. If you're going to tweet or post on Facebook, could you make sure your devices are on silent, please? There will be plenty of time for questions and answers at the end. Before we start, I'd just like to flag up a couple of other events we've got coming up. This time next week, we're holding a debate with the Department of Politics on the future of the UK post-Scottish referendum. So please do book online for that if you're interested. We have the Chancellor of the University coming the week after. And this Thursday sees the start of our Michaelmas Term seminar series, and it's on health in the 21st century. And we have Professor Peter Piot, who is the co-discoverer of the Ebola virus, and he's going to be talking about the implications for Africa and beyond. So please do go onto our website and have a look at what's coming up and sign up for more events. So that leads me on to introduce today's speaker. Professor Nick Bostrom has been with the Oxford Martin School for a long time now. He's director of the Impacts of Future Technology programme here, and he's also the director of the Future of Humanity Institute at the University of Oxford. I'm sure most of you are here because you've come across his latest book, Superintelligence. It's in the New York Times bestseller list for non-fiction, and we also saw today on Twitter that Elon Musk has recommended it as one of his top 9 books to read. So I think that's as much of an introduction as we need, and I'll hand over to Nick.
Thank you very much. Thank you. So this is the book there. Buy it if you haven't already. Buy several copies. Give to your friends, lest you live in a little bubble of enlightenment with nobody to talk to. I'm not going to try to summarize the book today, but I want to give some of the background where this kind of thinking is coming from. So with the Future of Humanity Institute and my earlier work, I'm interested in trying to figure out the broader strategic picture that we're operating in. The kinds of questions you would want to know the answer to if you wanted to know how you could do the most good in the world. And so if we zoom out and look at our current situation as a species from a very abstract point of view, we can maybe think in 2 dimensions, time on one and then on the other, some measure of technological advancement. And there is some band of level of technological advancement and economic productive capability that constitute what we now think of as the human condition, the modern human condition. It's worth reflecting that this band is a narrow segment of the possible conditions that could obtain. And clearly from an evolutionary point of view, the human species is a novelty in the scheme of things. But even if we zoom in and just look at things on a historical timescale, the idea that you wake up in the morning with an alarm clock and then commute to an office where you sit in front of a screen all day, that this is the kind of the lives that we're living is a huge anomaly on historical timescales. For most of human history, we were in something approaching a Malthusian condition, and only in the last few hundred years we've broken out of that. In spatial terms as well, the environment that we're familiar with, this little thin crust on the surface of one planet, is hugely anomalous in the larger scheme of things. Most is just ultra-high vacuum. And yet we tend to think that this is the normal way for things to be, and that if one wants to postulate that things could change radically, one faces an extraordinary burden of proof, because it would be an extraordinary hypothesis to think that the human condition could fundamentally change. But with this kind of picture, it's clear that the longer the timescale we're considering, the greater the probability that we will break out of it in one direction or another. And there are 2 ways that could go. So one possibility is to break out of it in the downwards direction. In population biology, there is this concept of a minimum viable population size. This is the idea that when you have too few surviving individuals, you get insufficient genetic diversity, you're too vulnerable to temporary shocks, and you go extinct. And similarly, with too low level of capability, we couldn't maintain human life, and we would then reach this attractor state of extinction. Once you're extinct, you tend to stay extinct. So it's a stable state. You can remain there indefinitely. I think there's another attractor state in this picture, which is one we could reach if we break out in the outwards direction. And the reason for thinking that there is a kind of attractor there is this thought that once you have a technologically mature civilization, a civilization that has developed all the technologies that are physically possible and important, then after that there might be no new risks from technology that could threaten you, and also you will have at that point initiated a cosmic colonization process where the species is spreading from solar system to solar system and galaxy to galaxy, and that kind of intergalactic empire is just a lot harder to see how anything would knock that out, and it might just continue to expand indefinitely until in the fullness of time it becomes impossible to reach any further material resources because of the cosmological expansion. So there is this big finite but large bubble of resources that could in principle be accessed from a civilization starting from our current spatial-temporal locations. Things that are beyond that, because the universe is expanding, are receding from us faster than the speed of light. So by the time you had sort of reached there, they would have slid further away. And that big bubble constitutes what I term humanity's cosmic endowment. It's the resources we could in principle access if things go well, and then transform into some kind of value structure, like flourishing civilizations with minds living for billions of years, the size of planets, thinking thoughts and having feelings that are literally beyond our imagination. But that too looks like an attractor state. If you break out there, you might be on a track, and you might with high probability end up at this cosmic endowment. And so from this picture, the concept of an existential risk becomes important. An existential risk is one that could threaten to cause the extinction of Earth-originating intelligent life, or to permanently and drastically destroy our potential for desirable further development. In other words, it's like a risk that could threaten our entire future. So it's distinct from all the other ways in which things can and do go wrong. So throughout history, there have been many catastrophes and calamities, from wars and earthquakes and plagues. But these have been merely ripples on the great pond of life. They haven't perhaps made any significant difference to the long-term prospects of our species. But an existential risk is qualitatively different. And there will only ever have been either 0 or 1 existential risk. So they pose distinctive challenges, which are interesting to think about, and one can come at it at different angles. One can think like an initial finding from this field of existential risk studies is that it looks like all the really big existential risks, at least if we're thinking about the timescale of a century or so, are risks that arise in some way from human activity rather than from nature. It's easy to see that we've survived risks from nature for 100,000 years, firestorms, earthquakes, volcano eruptions, and asteroids. So probably they won't do us in the next 100, but we will in this century introduce entirely new phenomena into the world that may pose significant existential risks. One way to make a similar point, but in a different sort of frame, is to think of, in terms of this metaphor of a giant urn, an urn of possible inventions, an urn of possible ideas. And throughout history, we have, as a species and as individuals, been reaching into this urn and picking out one ball after another, making different discoveries, introducing new technologies. And we can now look back on the track record of all this inventing, and we can see that it is good. The reason why we are now inhabiting this modern human condition, where we earn more than subsistence wages, is fundamentally largely because of technological progress. So most technologies have been good. Some have been mixed bags, like have had some bad effects, but some beneficial effects. It's actually not that easy to think of a technology that has been on balance bad, that we would have been better off without. But one can think of some plausible candidates for this, like maybe chemical weapons. You could argue the case that nuclear weapons we would have been better off without, like certain torture instruments. What we haven't seen yet is any black ball, like an invention such that it invariably spells the destruction of the civilization that makes it. We haven't pulled out such a ball from this urn. What could such a thing look like? Well, we can perhaps get some sense of what this kind of possibility would look like if we run a counterfactual. So a little over half a century ago, we discovered how to release the energy of the atom to produce nuclear weapons. And so it turns out that in order to do this, you need highly fissile materials, which are hard to come by. So it's hard to get highly enriched uranium or plutonium, and therefore it's hard to make nuclear weapons. You need large facilities that are expensive, take a lot of energy, a big footprint. So only a few states can really do this. And that was fortunate. Suppose it had turned out to be otherwise, that there had been some way to create a nuclear weapon by some simple method. Suppose you could do it by baking sand in the microwave oven or something like that. Where would civilization be now? Well, so we know that it's physically impossible to make a nuclear weapon by baking sand in the microwave oven, but before we had done the relevant physics, before we had actually done the atomic physics and particle physics, how could we possibly have known whether it would be easy or hard? So we reached into the urn, we pulled out the ball, and maybe nuclear energy turned out to be one of these gray balls, like big dangers, but survivable. But it could have turned out it had been a black ball. And in that case, probably that would have been the end of human technological civilization. Because if it became easy enough to destroy a city, then cities would get destroyed to a higher rate for that to be sustainable. Maybe human society would be knocked back to some earlier like Bronze Age stage, and when it clawed its way up again, it would again get the ability to make microwave ovens and to build nuclear bombs, and the cycle might repeat. We have a great ability to invent things, but we don't have a great ability to uninvent things. So once we have pulled the ball out, we can't put it back in. So far we've just been fortunate, perhaps, that we haven't encountered a black ball. And we don't know for sure whether the urn contains a black ball, but if it does, it looks like we're continuing to pull them out one after another. Eventually we will get it, and then that would be the end of it. So we can look more concretely at some possible technologies on the horizon that could possibly constitute such a black ball. I will talk a little bit more about AI in a minute, but there are others as well. Synthetic biology has obviously a wide range of very beneficial applications one can envisage, which is one reason for being confident that we will go forward with it and then face whatever dangers there might be. Molecular nanotechnology, not the kind of nanotech we have today, but if and when we get to the kind of nanotechnology like people like Eric Drexler have described, then that could be a source of great power. Various technologies that might make it easier to form and maintain totalitarian structures. I'm thinking maybe advances in surveillance technology or ways that makes it easier to manipulate and control desires through psychological or neurological techniques. Remember that an existential risk is not only one that could spell extinction, but also one that could permanently and drastically destroy our future. For example, by locking ourselves into some radically suboptimal state. Again, this could have a lot of beneficial applications as well, but it does seem that it has a potential downside. And I don't think that the state in political science is advanced enough to really tell us what would happen if it became a lot easier for a small group to run a big country without opposition. We know that technologies in the past have changed the kinds of political structures you get with agriculture, with writing, with gunpowder. This has a big ramifications on the kinds of political systems we have, so perhaps something like that could happen again. Human modification and geoengineering, and then a lot of unknowns there I think should be added. If we think about these existential risks that might seem large to us over the coming century or so, then we can note that they're all discovered or conceptualized only in the last few decades. So if somebody had asked 100 years ago what would have been the biggest existential risks, then perhaps none of the items on this list would have been mentioned. Maybe they would have worried some about totalitarianism, but they certainly wouldn't have worried about AI or nanotechnology before they had even computers. So if you combine this kind of picture with a lens of existential risk as helping us to focus on some really important critical feature, and with this other idea that there is a kind of weak technological determinism at play here, which I think is quite plausible. We get some interesting results. So what do I mean by technological determinism? Well, I don't mean that every detail about how technology goes is out of human control. What I mean is that if there is some fairly general purpose technology that has a lot of positive uses and that could be used among other things to make money or to heal people or to increase military strength, then it's likely that in the fullness of time that technology will get developed, provided that science and technology continues. One can think about it a little bit like if there is a big box that's initially empty and then we start pouring sand into the box. This corresponds to which kinds of scientific areas we prioritize, where we fund research. So where you pour the sand will then influence where the sand piles up in the box. But over time, if you just keep pouring in sand, then eventually the whole box will fill up, independently of where you sort of start to pouring it. It will spill over. So I think a similar weak form of technological determinism is plausible. So that means that perhaps the right question to ask with regard to some hypothetical technology is not, would we be better off with this technology or without it? Because it might be that that's just a fact over which we have no real influence. We will get it eventually. And that we need some other way to think about these kinds of things. So one attitude one could have in light of this is the one I think best expressed by this some commenter on some blog under the name of Washbash. He said, "I instinctively think go faster. Not because I think this is better for the world. Why should I care about the world when I'm dead and gone? I want it to go fast, damn it. Because this increases the chances that I have of experiencing a more technologically advanced future." So is Washbash right or wrong? Well, we have to be clear here about what the question is that we're asking. If the question we're asking is, what would be best for me from an egoistic point of view, then I think that Washbash quite plausibly is right, that we would have reason to hope for faster technological development. The default is that we all die from old age in just a few decades from now. And the only way to even have a chance of escaping that, if we're thinking about this cosmic endowment that humanity has and like astronomical lifetimes or uploading into computers, something like that, the only way that that could possibly happen is if there were rapid technological progress and then some massive breakthrough that we don't think looks very imminent happen somehow, like AI or a cure for aging or some other like radical shakeup. It's the only way that that could happen. So if that's what you're holding your hope for, then you would want maximum progress just to sort of stir things up as much as possible to avoid the default fate of just kind of rotting away and dying from old age or prematurely from some other disease. Even if you don't wish for that, you just want faster technological progress in order to maybe inhabit a wealthier future with cooler gadgets, which we'll see more of with faster progress. But if instead we're asking a different question, not what's best for me, but what would be best from an impersonal point of view, then I think the attitude would be different. We might want to then embrace something like what I call the principle of differential technological development, which states that we should retard the development of dangerous and harmful technologies, especially ones that raise the level of existential risk, and accelerate the development of beneficial technologies, especially those that reduce the existential risks posed by nature or by other technologies. So the idea here is that even if we have this weak technological determinism, it doesn't mean that what we do is irrelevant. We might not be able to permanently prevent some possible technology from coming into existence, but we can make a difference to when it comes into existence. If you thought we could have no influence on when a technology comes into existence, then we should presumably stop funding technological research altogether, because it would just be a waste of money. If technology development were going to happen exactly in the same way, whether we poured money on it or not, we might as well save the cash. So presumably, we agree that it's possible to maybe make some technology available a few months earlier than it otherwise would, or a few months later, depending on how much we prioritize that research area. And then this principle of differential technological developments suggests that instead of just trying to focus on the possible benefits we could get from different technologies, we should try to target our efforts in technology to maximize the difference between the existential risk reducing technologies and the existential risk increasing ones. So that will be relevant when we are thinking about artificial intelligence in particular and superintelligence more generally. There are kind of two possible ways we could get to some form of superintelligence. We could imagine enhancements of biological intelligence. This has happened in the past over evolutionary timescales, big leaps in the sophistication of information processing, most recently with the emergence of the human species. But there is no reason to believe that we have hit the limits of what is possible with biological processing. Far from being the smartest possible biological technological species, I think we are probably the stupidest possible biological species capable of technological civilization. It's more that we started from a low level of intelligence and then gradually grew smarter, and once we reached a sufficient level of intelligence to do technology, we did it. And so that's the level at which we kind of are now, the lowest level of biological intelligence that is sufficient for unleashing a technological civilization. But there's no reason to think that we've anywhere close to limits. But the timescales there seem to be very slow, at least if we leave things to nature, and they could go in the other direction as well, of course. The other path is through machine intelligence. Machines right now are far inferior to us in general intelligence, but they are improving at a more rapid clip, perhaps. So we can ask about which of these will get there first. And more specifically, one can consider different ways of trying to create superintelligence. I'll talk a little bit about biological enhancement in just a second. Networks and organizations is also important. This is the idea that in addition to trying to enhance the performance of individual brains, we can also try to improve humanity's epistemic performance by getting better at aggregating information and having better institutions for stimulating collaborative efforts in science and technology and having more of us. But I won't talk really much about sort of this kind of collective form of superintelligence today. Then there are these hybrid approaches, the idea that you would somehow create something that has the best features of machine and man by like implanting chips in the brain. And personally, I think this cyborg path is not really very promising at all, because it's going to be very difficult to significantly enhance the capabilities of a normal, healthy human being by implanting stuff. You could get almost all the benefits that you could have from a brain implant by having sort of the computer outside of yourself. And like, so I get asked, like, wouldn't it be great to just be able to access Google by just thinking about it? But I mean, I can already access Google. We have these wonderful interfaces already called like eyeballs that can project 100 million bits straight into the brain per second with dedicated neural machinery to interpret this sensory information. It's really hard to do much better than that. And at the end, I mean, it's not as if the rate at which we can pump sensory information into the brain is the bottleneck. The bottleneck is our ability to interpret and make sense of that information. So the first thing you do with these 100 million bits is to throw almost all of it away, and you try to extract higher level features to then make a representation of the visual world. So I think for some people with disabilities, it can be like promising perhaps, but it's hard to see how it would significantly enhance the performance of healthy folk. And then we have machine intelligence, which I'll also come back to in a second. But just to put in a little bit more detail about the biological cognitive enhancement path, I think that the place where that will first become technologically feasible is likely through embryo selection. In the context of in vitro fertilization, a couple generally produces some number of embryos, maybe 8 or 10 embryos, and the doctor then chooses one of those to implant. And today that can be done only with some simple criteria. So if an embryo looks kind of abnormal and strange, you wouldn't select that. You can test for various monogenic disorders. You can't currently select for any interesting complex behavioral trait. But the price of gene sequencing is now falling very rapidly. And it is becoming possible to run these really large-scale studies with hundreds of thousands of subjects, and soon with millions of subjects, that will be necessary to determine the genetic architecture of the variants that we see in human intelligence, more specifically the additive component of the variants of human intelligence. And so once we have that data, then you would need no other new technology. You could just use that data to do this discrimination if you wanted. So there are various kind of ethical issues around this, which I will not talk about today, not because I don't recognize that they are there, but I just want to first focus on like what would actually be technologically feasible. There is then another technology that would vastly potentiate this simple, straightforward embryo selection, but it would require something new. This is the idea of iterated embryo selection. I wrote a paper last year with Carl Schulman where we tried to analyze this scenario. So here you would do embryo selection, but you would have this additional technology of being able to extract stem cells from an embryo and then use those to produce new sperm and ova that you could combine into new embryos, so that you could, in effect, collapse the human generation cycle from 20 years or 30 years down to maybe a month or two. And instead of facing the problem as like the old eugenics movement advocates did, of trying to persuade some large group of people to change their breeding patterns and keep doing that for a few hundred years, you would now have a situation where you could, instead of having centuries, you would be doing this within like a year or so, and instead of changing people's mate choices, you would just have a petri dish. So the feasibility would increase rapidly. And so the missing technology here is the ability to grow gametes from embryonic stem cells. Now, this has been done in mice, so it's not a science fiction technology, but it has not yet been perfected to be suitable for use in humans. So there is some uncertainty as to how long that will take. But if you had that, then you could do multiple generations of embryo selection within short timescales. And we did some calculations of the amount of selective power that you could get with different assumptions here. So if you imagine just producing two embryos and you select the one that looks like it has the highest disposition towards some trait like intelligence, you could select for all kinds of other things as well, like obedience to authority or health or whatever. But we're focusing on cognition here. If you select the best of 1 in 2, you might get something like 4 IQ points on average. If you select 1 in 10, you get somewhat more. And if you could select 1 in 100 or 1 in 1,000, you get a little bit more. But you see that there is a rapidly diminishing returns here. So just increasing the size of the pool of embryos that you select from gives you less and less. So it's hard to scale that. By contrast, if you have this iterated embryo selection going, then the total number of embryos that would be involved could be much less, and you would still have a much bigger effect. So by having 5 generations of selecting the best of 1 in 10 for each generation for 5 generations, where 1 generation might be 2 months, you might get as much as 65 IQ points. And with 10 generations of 1 in 10 selection, that is involving 100 embryos in total, you might get a genotype that would be expected to produce a phenotype beyond what you've seen throughout human history. Like there might just not have been any person in all of human history with that kind of propensity for intelligence, like some sort of super von Neumann type of entity. So already with this, it looks like some kind of weak form of superintelligence would be feasible. And it might be that there will be other genetic engineering approaches that will kind of overtake this selection approach. This is still quite wasteful. You're producing a lot of things and then selecting one. It might be that with new techniques like CRISPR and other forms of genetic engineering, if they could be made precise enough, you could get the ability to design a genome to specification, and you could then get even more. So there are some reasons for thinking that not only are we far from the ultimate limits of biological in information processing, but that we might, within the foreseeable future, foreseeable here meaning we could maybe start doing this in 10, 15 years and have much more advanced capabilities within a few decades, that we could reach some kind of weak superintelligence. So this then is a kind of alternative to machine intelligence. And I sometimes and presented with a suggestion that if there really are these big risks related to machines becoming smarter than humans, as I argue in the book, that maybe this is a reason then for pursuing biological cognitive enhancement, so that we could keep one step ahead of the machines. I think that's fundamentally misguided, and that pursuing the biological cognitive enhancement path will not delay, but will instead hasten the day when we are overtaken by machine intelligence. Because with smarter humans, you will have smarter computer scientists doing the AI research, and they will meet with success sooner than we would do if we were approaching this with current capabilities. So cognitive enhancement, I think, will speed our approach to the time when machines overtake us. There might nevertheless be good reasons to pursue cognitive enhancement. And I think, on balance, there is, basically because we would want whichever generation it is that eventually creates superintelligence to be as competent as possible. But it would not be that we would keep ahead of the machines. It would be that we would be more skilled when we are creating them. That would be the basic reason for favoring cognitive enhancement. But either way, we will at some point, I think, face the challenge of machine intelligence. When most people think about AI, like there are various kind of milestones that spring to mind. These are occasions where there is some visible achievement in the field of artificial intelligence that's dramatic enough to kind of make a blip on the radar of public awareness. The defeat of Kasparov by Deep Blue was one of those. Self-driving cars, sort of legged locomotion, robotics, and most recently, perhaps, Watson's trouncing of the human all-time Jeopardy champions. This is a sort of trivia quiz show. Are these occasions where machines have made some big advance, and suddenly it looks like maybe AI is much closer than it looked before. But these are not necessarily very good metrics if one really wants to have some sense for how much the field is moving forward. Underneath the hood, sort of driving these advances, are a number of techniques in AI and machine learning that have driven the progress we see. And a lot of the actual uses of the AI are kind of more or less hidden from view. There is like a saying among AI researchers that as soon as something actually works, it's no longer called AI. It's kind of frustrating. But a lot of we just think of it as software, like boring software. And there is a tendency for the goalpost to move. It used to be the case that chess was regarded as sort of the epitome of human intellection, this deep game that required deep strategic thinking and planning and creative problem solving that some people thought would be forever beyond the reach of machines. But once they did it, then we kind of downgraded chess. It no longer seems like it's just like computation. What's the big deal? And so there is this sense of moving goalposts. But there have been a number of these techniques that have been discovered, most of them in the last 60 years or so, since we got computers. A few key developments done before that, like logic. And concomitantly with that, also just the growth of hardware power has been fueling these advances. And if we look at particular domains where it's possible to measure these things, like chess is one of them, it seems that roughly half of the progress in chess computing that we've seen is attributable to hardware getting better, and roughly half of it is attributable to our algorithms getting better and databases. And as a rough rule of thumb, that seems to hold for a few different domains. The exact proportions might vary somewhat, but certainly both hardware and algorithmic improvements have been very important drivers of progress. So one possible path towards machine intelligence would be that we discover some more of these basic techniques, enough so as to gain the ability then to engineer, to craft a synthetic artificial intelligence. And we don't know how many of these additional discoveries would be needed. I mean, we certainly know we can't do it today. So at least one more of these, probably several more at the minimum would be needed. But whether we need sort of an extra 5 like great new ideas in this field, or whether we need 20, that's very difficult to estimate. So we just need a broad probability distribution over how many remaining discoveries would be required. An alternative approach to machine intelligence is to try to crib from nature. So we know there already is a general intelligence system, the human brain, and we can study it and try to decipher how it works. See what computational architectures are employed in the human brain, what learning algorithms, and then use similar things in a computer. And this can come in various degrees. On one hand, you would just draw some loose inspiration from nature. You see that, well, the brain is a neural network, so maybe we should explore neural network-like structures. The brain uses reinforcement learning algorithms, so maybe we should explore reinforcement learning algorithms. But where there is no particular attempt to get the details right, to be biologically realistic. At the other end of the spectrum is whole brain emulation, where you would literally try to copy a mind without necessarily understanding how it works. So the idea there is that you would take a particular human brain, freeze it or vitrify it, and then slice it up into thin slices. You would feed those slices through an array of powerful microscopes to image them at sufficiently high resolution. Then you would create a stack of these images and use automated image recognition software to extract the 3-dimensional connectivity matrix. That was originally implemented in the biological neuropil of the cortex and now exists as a data structure. Combining that with computational models from computational neuroscience of how different neuron types work, and then running this whole thing on a sufficiently powerful computer. This is something that we are very far from being able to do today. So by contrast with this, where it's hard to, we can't really be 100% certain that no clever person somewhere in a garage somewhere couldn't like find a great breakthrough tomorrow. It looks low probability, but we can't really rule it out. With this, we can kind of be sure that it can't happen in the near future, because it would require some very powerful enabling technologies that we don't yet have. On the other hand, the whole brain emulation approach would not require any great theoretical breakthrough, any deep conceptual revolution. It would only require incremental advances in a number of technology areas, microscopy, automated image processing. We already have good neurocomputational models of many types of neuron. We would need to expand that library. So there's maybe a higher degree of confidence that we could eventually get to the goal by kind of studying the human brain or copying it. But it might be that we will get there faster through this purely synthetic approach. These pictures here kind of represent the state of the art. Up on the left there we have an electron micrograph of a slice of neural tissue where you can see, if you look carefully, cross-sections of axons and synapses. So this is the kind of resolution you would need. You would need some more information, probably, than is in this, this kind of picture. We already have microscopes with sufficient resolution. I mean, we can see individual atoms if we want to, right? It's just that if you wanted to image an object the size of the human brain at atomic resolution, it would take forever to do that. So you need like advances in high throughput microscopy and so forth. This is a block. It's just what you get if you put a lot of those pictures together. And this is the result of image recognition software operating on this kind of information. And you can see that it has extracted the connections between the different neurons there. But the result is not really good enough. It often makes errors in drawing out these connections. And it doesn't tell us which connections are excitator or inhibitory or what the strength of the connections are. We have a simple model organism, C. elegans, which has exactly 302 neurons. And we have the entire connectivity matrix mapped out for C. elegans, but we still can't really emulate its behavior because we still lack some of this information about the nature of the connections. So C. elegans, 302 neurons. The human brain, 80 billion neurons. There is some ways to go there. But it might be that once you reach a sufficient level of capability, the last bit is just scaling it. So But it's a kind of technology where you would expect to get some fair amount of advance warning. You might be able to succeed with a mouse before you succeeded with like a chimp brain, and with a chimp brain before a human brain, and you would probably need a large industrial scale facility to do with this. It would be very surprising if this could happen in less than several decades, and it might take longer. Whereas with the synthetic AI, there is a wider probability distribution. So I'm not going to go into this, but yes, as I suggested, AI is used, machine learning is used in many different sectors of the economy. And recently there have been a kind of a big wave of enthusiasm washing over this field with a number of sort of high-profile acquisitions. Here in Britain, maybe what was the world's leading AI company before, DeepMind, that we were doing work with, were bought up by Google earlier this year, or was it last year, late last year or early this year, and there's some competition for talent in this field. So this is one reason perhaps to think that like things are moving right now. On the other hand, in the history of AI, we can look back and we've seen that there have been about 2 of these sort of hype waves before, where there was great enthusiasm and big expectations and followed by disappointment. So this is maybe the 3rd great wave of enthusiasm, and maybe this will be it, or maybe it will be followed by disappointment, and maybe by another wave of enthusiasm and disappointment. We don't know how many of these waves will occur before we finally actually get there. There are some particular domains which we can identify where AIs are already far ahead of humans, like game AI in many games are in this category, but they are still far beneath us in terms of common sense, general learning ability, creative problem solving, and many other things that are essential. How far away are we from human level machine intelligence? We did a survey of some of the world's leading AI experts last year, and this is what we found. One of the questions was, by what year do you think there is a 50% probability that we will have human level machine intelligence? And you can see the median answer to that was 2050 or 2040, depending on precisely which expert community we asked. This, to me, seems somewhat reasonable. I think there's a big uncertainty on both sides of those years. Like, it could happen much sooner, or it could take much longer as well. We also asked, by what year do you think there's a 90% probability that we will have human-level machine intelligence? This is conditional on there being no collapse of human civilization. And here I would disagree. I think it's over-optimistic to assume that there's or pessimistic, depending on how you look at it. I don't think there's a 90% probability that we will have human-level AI by 2070. We just can't have that level of confidence in these technology forecasts. So that seems overconfident. We also asked how long you think it will take, if and when we do reach human level of machine intelligence, until we get superintelligence. And the median probabilities assigned to this was that there was maybe a 5 or 10% probability that would happen within 2 years after human level machine intelligence. So there I disagree. I think that I'm quite agnostic as to when we will have human level machine intelligence. I just don't think we have information that enables us to have a very sort of peaked probability distribution for that. However, I do think that if and when we do reach that point, there is a fairly high probability that we will shortly thereafter have superintelligence. Certainly more than 5 or 10% probability. And I don't really have time to sort of explain in detail why I think that, but one intuition is this, that although we might naively think of human intelligence as this like wide range from like the village idiot at one end and Einstein at the other, and that there's like a huge difference. I think that a better picture of the situation is like the one here on this slide, where right now we have AI that's the equivalent of, well, you can't really make these exact mappings, but if we had to, maybe we could say current AI is on the level of a bug or a bee or something like that. maybe if we keep working hard in this field, we will eventually get to like mouse level AI. And then maybe if we keep working hard for a long time after that, we'll get like up to chimp level. And then if we keep working hard for a long time after that, eventually maybe we get up to the village idiot level. But then I think that we'll just swoop right past Einstein. If you think about Einstein and village idiot, from a basic neurological perspective, they are basically identical. I mean, they have the same brain. You can hardly see any difference. Roughly the same number of neurons, same number of connections, the same speed of information processing in each neuron. And so in terms of absolute difficulty, there's no reason to think that it would be much harder to make an Einstein-level AI than a village idiot AI. And then beyond that, something that is like far greater than Einstein. So there's a lot more to be said about that, but here I just want to make this point that it's important to distinguish these two questions. The question about how far are we from AI now, and the question of if and when we do get to that point, what does the future then look like? How quick will this transition be? How steep will the transition be from human level to superintelligence? This second question is significant in at least two ways. So if we have a fast takeoff scenario where the takeoff here is on the scale of minutes or hours or days, some short period of time, then it's clear that whatever safety mechanisms that we want to rely on will have to be developed before the AI is created. There's just no time, like once the AI is starting to do some dangerous things, to try to develop a whole new safety system if you have like 16 minutes to do it. So in a fast takeoff scenario, the control problem has to be completely solved in advance. And you don't just have to rely on the mechanism being set up correctly so that once it goes off, it will unfold in a desirable direction. If we were talking instead of a slow takeoff scenario where you get to the human level, but then it will take decades or centuries to sort of gradually claw our way up from there to genuine superintelligence, then you could imagine that we would have time to develop global institutions to deal with this, to institute new PhD programs, to train people in like AI controlled technology, to see what works, and if something doesn't work, we try something different. So one way in which the steepness of the takeoff is relevant to us today is in terms of it bearing on the question of how much work will we need to have done in advance. And another way in which it is relevant is that if you have a fast takeoff scenario, then you're going to end up with a world where you're much more likely to have a singleton. That is a world order where at the highest level of decision making there is only one effective decision making agency. So think about it like this. You have different companies competing, or different countries on some technology project, whether it's to launch some new kind of software or develop some new kind of weapons technology. And sometimes there are races to develop the technology first. And sometimes those races are quite close. But by close, we here mean that the leader might be like a few months or a few years ahead of the follower. This is what we see with like nuclear weapons, ICBMs, and like a lot of other technologies. Two companies being close doesn't mean that one company is likely to succeed 5 minutes ahead of the others. There's going to be some reasonable like human timescale difference between the leader and the closest followers. So if you have a takeoff that is over in the course of hours or days, then you're likely to have a situation where the leader will have started the takeoff and completed it before the follower, the closest follower, has even started it. And so you then have a world where there is a mature superintelligence and no intellectual peer, no other system that is even near it in cognitive ability. And this world that is then contains this single superintelligence would be one, I think, likely to result in a singleton. This first superintelligence would be extremely powerful, able to develop all other kinds of technologies that we could have developed over tens of thousands of years, but do them very quickly on digital timescales, reach technological maturity, and then shape the future according to its desires. So either the AI itself or the product that controls it would then end up maybe in a position to just shape the future according to their preferences. By contrast, in slow takeoff scenarios, you're more likely to end up with a situation of economic competition or a situation in which evolutionary dynamics operate on a population of digital minds. You will still end up with minds that are super intelligent, but at no point will any one of them be so far ahead of all the others that it can just lay down the law. Instead, you'll have a population of gradually increasing capabilities. And the concerns in that type of multipolar scenario look very different from the ones in the single zone scenarios. Not necessarily less serious, but quite different. So I'm aware of the time ticking here, and so I'm going to wrap up. So what I've said so far is really just setting the stage. The great bulk of the book is really about what happens if one has this picture. How could you try to control the outcome of an intelligence explosion? How could you try to engineer artificial agents so that they would behave in some predictable and desirable way as they grow into superintelligences? What could we say about what a superintelligence would want to do? Can we analyze that at all? And we can say some interesting things about that. And then, most importantly, this is the last couple of chapters, what does all of this mean for what we should be doing today? Like, how can we, if we think that this is the kind of end game, although we're very unsure about the timescales for that, how should that affect what we want to do now, insofar as our desire is to do what would be best from an impersonal view, to do the altruistically optimal thing, which turns out to be a highly non-trivial question. But I'm very eager to have a little discussion and Q&A, so I'll stop there. Thanks.
So Nick is going to take your questions now. So if you could raise your hand if you have a question, and Nick will point me in the right direction and I shall bring the microphone over to you. Please be aware that we're also filming and live webcasting the Q&A as well. So just be aware of that when you ask your question.
Okay.
Thank you very much for the extraordinary exposition. I'm just curious why on this graph the map, the line flattens off once superintelligence has been achieved.
Yeah, so the idea is that there are ultimate physical limits to information processing, which we know that there are. A given amount of matter in a given amount of space can only contain so many bits and can only process them at such a rate. So there is some ultimate limit beyond which you can't make further progress intensively. That is by changing the configuration of the system. At that point, the only way to further expand your capabilities is by acquiring more resources, physical resources. You need more matter to build more processors. And that can maybe in the short term happen at a very rapid clip, but in the longer term, it's limited to a polynomial rate in that we have the speed of light limiting the rate at which astrophysical resources can be acquired. So the long run development of this kind of system is that you're growing at some significant fraction of the speed of light in all directions and gobbling up more planets and galaxies as you go along. But that will then create a growth rate that is polynomial rather than exponential. So it will look like it's slowing down compared to the exponential phase. Or there's no reason to think this will be exponential, actually. I mean, it just looks steep. There's this kind of tendency to call everything exponential in this field, by which people really only mean fast. It would be better off, I think, reducing, calling everything exponential, that's fast. Yes, yes, and then we'll try something further back after that.
Yeah, thank you for an amazing talk. You had a slide earlier where you showed people's predictions, or several organizations, I guess, predictions of when human-like machine intelligence would be achieved. I was wondering if you could unpack it a little bit. It would be interesting to know at the present who is more optimistic, who is more pessimistic, and in your opinion, why, as in technologists versus scholars versus investors in AI. I was just not sure what the acronyms on the left-hand side were standing for.
Yeah, well, so I should also say these are small sample studies. So in addition to actually just, in the end, being the subjective judgments, which obviously makes them unreliable guides to the future, the survey methodology itself is fairly weak. I mean, we did the best with the resources we have, but we don't, better studies could be done. There are no very drastic differences here. This is some kind of philosophy and theory of AI scholarly community, more European-based, focusing on cognitive systems. Then AGI are some people who are specifically working on AGI, but not very mainstream or prominent. The EETN, that was some other conference. I forget exactly what it is. The top 100 were only a subset of those responded, maybe like 25% or something like that. These were identified by publication metrics, so the most distinguished people in AI. And combined, it's just all of the above. So I think the two most significant rows are top 100 or combined. So I don't think we had enough of a sample to reliably tell different subpopulations apart. My gut feeling is that there seems to be maybe less boosterish expectations in Europe than in America. It's like American AI community seems to be more like we could do something cool here, whereas the European is more, oh, well, we don't understand embodiment. We need to think about what it means to have a body. Like, some people in industry are very boosterish. Some people focusing more on cognitive systems, less boosterish. So there certainly are big differences, but I don't have any actual data on that. I think you there in the back. Yeah.
Thanks. I think it's a fantastic point when you say there may seem like a wide gap between the village idiot and Einstein for us, but when we take a wider perspective, actually, they're relatively close together. However, I partially agree and partially disagree when you say that this means when we reach the machine intelligence level of the village idiot, it's going to be very quick to get to Einstein. So your point was that Einstein and the village idiot use the same machinery, as it were. They have the similar brains. However, doesn't this suggest that because the brains of the village idiot and Einstein are capable of such different things, that there's something wider to the problem which we're not quite grasping yet? And do you think this is an interesting way of looking at it in terms of how we might then solve the problem? The fact that we have very similar brains with very different things that they can achieve.
Yeah, I mean, so we can certainly infer things like just having 80 billion neurons connected somehow is not enough to get Einstein level. I mean, we know it's not even sufficient to get village idiot. The details matter there. But I think we have to get the details right to get even to the village idiot level. Like, you need not just to have some kind of oscillating neural network that looks like it has sleep-wake cycles. You need to actually have something that specifically encodes information by learning and then generalizes from that. So that's part of the motive. There is another, so to some extent, the argument for how confident we can be, and I'm not absolutely confident in this fast takeoff scenario. I just think I would assign it more than 50% probability. It also partly depends on the architecture, and which we still don't know which kind of architecture will first reach the human milestone. So the kinds of improvements that would be easy to make after that might depend on the architecture of the system that got there first. But there are certain kinds of improvements that could be applied to any architecture. So if at this point in time you still have, say, something like Moore's law happening, which you might or might not have, then one way to improve the system is just by running it on faster hardware or on more processors. And you could get a kind of speed superintelligence from that. And depending on like how much you spend on the computers to create the human level performance, that might or might not be easy to scale the system further. Then there's another variable that comes in here. So to analyze the kind of the takeoff dynamics, on the one hand there is the recalcitrance, which is what I've been focusing on, like how difficult is it to improve the system. The other factor is the optimization power, the amount of effort, quality-adjusted effort going into improving it. And there I think we can have good reason to think that it will certainly not be reduced, but probably increase once we get human level intelligence. I mean, certainly from an economic point of view, once you have a system that actually works at human level, that would be massive economic incentives to make further improvements. Human labor is 70% of the world economy, and once you have something that substitutes for human labor, any improvement you make immediately applies to 70% of the world economy. And at some point, above that level, let's see if we have this. So this would kind of, the human incentives to start working hard on the system would apply already here and to some extent in the run-up. But once the AI becomes smart enough, then you have an additional factor. You have a feedback loop. So at that point, the AI itself will be contributing to its own development. And as it gets smarter and smarter, at some point, maybe the bulk of the optimization power being applied to the system is coming from the system itself. And from that point onwards, whenever the system is improved one step further, the amount of optimization power going into it is also increased. And you get this feedback loop, which adds to the kind of the possibility of an explosive outcome. Maybe.
Thanks, Nick. You know I'm a great supporter of your work. I think it's fantastic that you're doing it. But what would you say to the skeptic who says, look, you're facing a kind of bootstrapping problem here? If you look around the world today, in the billions of dollars that are spent on, say, a simple problem like cholesterol or deriving stem cells to treat disease, and the huge number of brilliant minds that are put on, they can't solve these kinds of problems. Yet you're talking about cosmic endowment and these enormously complex problems, and there's a small group of you, working away with a whiteboard. Why should we believe any of these projections, given the sort of complexity of the issues that you've discussed? I mean, why should we, for example, believe in that graph that you've got in front of us there?
Well, I think there are kind of two possible answers to that. So one is just to look at the object level. At any particular paper, has to be validated on its own merit. So it can be critiqued or supported like any other academic paper, and it should be. On the meta level, though, I think the question is not so much can we be confident that we have it right, but rather what is the alternative. So I think we're already making a lot of decisions that will have long-term consequences. Sometimes we try deliberately to take those long-term consequences into account. For example, when we are concerned about global warming or something like that. It's obviously not because what global warming will do within the next 10 or 20 years. Like, if it would never get worse than it is within the next 10 or 20 years, it wouldn't be worth worrying about it. I mean, the only possible reason for being concerned about it is that if we think, like, towards the end of the century, maybe things could be bad, or we're worried about the solvency of the pension system, or we are worried about whether we're spending enough on basic science, that doesn't have any immediate payoffs over the next few years. Like, it's because we have some views about what long-term will tend to lead in desirable directions. And a lot of these times, there are assumptions in these kinds of reasoning that are not brought up to the surface and examined. And those assumptions might be very naive and misguided. And so we're making all these efforts to try to affect the long-term future, but without ever having really to reflect it carefully about some of the basic assumptions underlying all those endeavors. And so one of the things we want to do is to try to surface some of the assumptions, subject them to critical analysis, do as much of that analysis as we can on them, and then present exactly what the reasoning is. And hopefully that will enable humanity to be more sophisticated about how it thinks about its kind of macro strategy. I am, though, I should say, personally very concerned about the possibility that we might just be sort of hopelessly in the dark about these things. Because it does look like we made a lot of progress on thinking about these things over the last 10, 15 years, and are still making rapid progress, but that also suggests that there is a lot more progress that remains to be done. And if that progress that remains to be done will change our view as much as the progress that has been done in the last 10, 15 years has changed our views, then we must conclude that our current views are probably very misguided. So I do think it is true that we are substantially in the dark, and figuring out sort of wiser ways to behave in this epistemic predicament is a very high value activity that I'm hoping to devote some attention to. Maybe there's a gentleman next to the wall.
In iterated embryo selection, I can imagine how you would shorten the generations to 1 or 2 months. I didn't understand how you would select for intelligence in those few cells or lumps of cells.
Right, so the idea would be to take an embryo, I guess at the blastocyst stage, extract one cell, sequence it, and then use that to form some estimate of the potential of the embryo for manifesting the trait value that you're interested in selecting for, which could be anything depending on who you are, and different cultures might have different attitudes to this, whether they permit the technology to go forward or not. Does that answer your question, or?
Well, it's basically indirect. Based on DNA data knowledge you have, you would estimate. So based on DNA knowledge you have, you would estimate that this sequence is more intelligent, but you wouldn't know.
Yeah, I mean, so we know, I mean, so there are a lot of these, like, tons of studies trying to figure out to what extent different psychological traits are heritable or not. With like twin studies, and more recently you have more sophisticated ways of doing this. And particularly on cognition has been the focus of a lot of that research. So we have some range of estimate of how much of the variance is due to environmental differences, which differs in different environments. So generally, less depends on the environment once the environment is pretty good, like in a kind of modern development. Anyway, so those are the kind of data that would go into that kind of analysis. Yeah, do you want to?
I've got one from Twitter.
Oh, okay.
As we're doing.
Let's hear what Twitter has to say.
So Jay Stockwood has asked, are the existential risks mentioned taken seriously by governments, and what are they being doing to create a controlled detonation?
Are the existential risks taken seriously by government? Generally speaking, governments, like most people, haven't tended to differentiate very sharply between existential risks and other global risks. Like, something that could destroy our country and something that could destroy humanity is roughly equally bad, it seems, in the qualitative thinking of most people on these issues. So hence there hasn't been much of a focus to specifically figure out which things are existential versus just could pose big problems for the global economy. On the control problem, no, the governments have not done anything on that. And I think it would kind of be very premature for governments at this stage to try to do anything much on that. What is most needed right now, I believe, is technical research in theoretical computer science and mathematics, and with some fractions of some other disciplines like philosophy can be helpful towards this control problem. So that by the time, whenever that is, that the solution is needed, we will have one at hand. And it would be too early to try to get some kind of regulatory intervention, I think, that this field.
If we just take one more from the floor, and then Nick is going to be signing books afterwards. So if you have any questions, when you're getting your book signed, you can ask him then. Sure. And there is be a drinks reception that Nick is going to be present at as well. Okay. So just one more question from the floor.
Okay, well, maybe the lady there and the... Hold on.
You talked of the principle of differential technology development, where we could retard the development of dangerous technology and accelerate the development of beneficial technology. My question was, like, many times technology is developed and it's much later usually everybody develops with a beneficial view or a for-profit view. It's much later you realize that it has negative impacts. So how do we apply this principle? And the second question I wanted to ask is that in the near future, do you see like governments and companies applying this principle?
Well, so with the principle of differential technological development, it's not so much that it's clear that we should try to retard various technologies. It's more that, that this might furnish a criterion that we could then use to evaluate different proposed actions or interventions. So it might be that it's just very hard to make much difference by slowing down the technology. Like if you're a small group, like an individual philanthropist or like some guy, like you might just not have much leverage over that. It might be a lot easier to accelerate. So for example, if there is the problem of making progress towards AI to actually make machines intelligent, and then the other problem of how to ensure that intelligent machines would be safe, it's really hard to make much difference to how rapidly the world is moving forward to develop AI. It's a lot easier to make some substantial difference in how rapidly we are moving forward towards a solution to the control problem, just because there are so few people working on that. And a lot of people would oppose you if you try to slow down AI, but nobody opposes you if you want to speed up progress on the control problem. So it just seems that applying this criterion to this case would suggest that you should focus on like accelerating progress on the control problem. Now, notice that this is restricted to technologies that pose existential risks. So there are all kinds of other risks that all technologies face. This is not meant to be a very fruitful guide to all of those. So one of these implicit assumptions I mentioned in my reply to Julian that our thinking about global priorities rely on is the assumption that we want more innovation. I mean, the whole kind of university ethos is like, let's discover more things. We can make more progress in science and technology, and knowledge is good, and the more is better, and the faster we get it, the better it is. That itself is one of these assumptions that is less obvious when you start to think about like the overall strategic situation, and it might need qualifications. But if one were not concerned with existential risks, but just with the kind of pros and cons at more limited scales, then I mean I would put it that overall the track record of technology has been immensely good on balance, and that we would want faster growth just to reach more and more of these benefits sooner. And it's really only when you're sort of thinking about the possibility that we fall off the cliff, I think, that you might want to have a more nuance to you, or maybe certain technology areas are actually ones where we would prefer the key breakthroughs to come a little bit later. Okay, so I guess we'll have to wrap up now, but I'll be happy to maybe answer some few more questions over the book signing process. Thank you.
And join with me to thank Nick for his amazing talk.